let's start now with reminding you what we did last time. So last time we introduced Hilbert space and states in Hilbert space, and then we defined bases and linear operators in Hilbert space, and then we also defined some families of linear operators which are useful and which we will see every now and then. And in particular, there are two things that I didn't say explicitly, which I'd like now to tell you as an additional add up from last time, just that you exactly know these things. I actually, when I prepared the first lecture, I thought that you know this for sure, but now I'm not sure. So let me just give two details: one about the inner product, and the other one about linear operators and their Emission conjugate. So as a recap, first I'd like to state some properties of the inner product. So the inner product, which is a map from element of Hilbert space, so from two elements of the Hilbert space to the complex numbers. And this map has the following properties. So first, it's linear in the second component. Okay, so if we have, say, for V and Wj in the Hilbert space and say Aj in the complex numbers, we have first, okay, linear in the second component, which means that V, the inner product between V and the sum over J, Aj, Wj is equal to the sum over J, Aj, and then the inner product of V and Wj. Okay, this means this linearity now in the second component. In the first component, it's conjugate linear, and the reason is that we have V and W is equal to W V complex conjugate. Okay, so this means complex conjugation. And now you see, if you put these together, it's not linear in the first component, but it is conjugate linear, meaning that you get out here then the complex conjugation. Okay? This is, I think this is the usual way how you define an inner product in a complex vector space. And then the third property is that the inner product between two states is always greater or equal to 0 with equality if and only if V is the 0 vector. Okay, so I don't know if you have seen this before. If with 2f means if and only if. Okay, I think I'm going to use this several times. Okay, this is a recap for the inner product, and then we also discussed Emission conjugate operators. And I think I didn't tell you exactly how you calculate this once you have the outer product representation. So suppose we have a linear operator A on the Hilbert space H with the outer product representation. So we write A as sum over J, K, and then the elements A, K, J, VK, Vj. Okay, this was the outer product representation that we introduced the last time with matrix representation AKJ, so these are matrix elements. And then the Emission conjugate is calculated, so let me write this down. You calculate this such that you transpose and you complex conjugate. Okay, so you have the sum over Jk, and then you complex conjugate the elements A, K, J, and you do a transposition, which leads to transpositions here. You switch these two, the bra and the cat. Okay, this is a transposition, and then you do a complex conjugation. And that's why the Emission conjugate is often also called simply the conjugate transpose. Okay? So just as a reminder how to calculate this, because we're gonna have to use this several times. So with this, I'd now like to start with the topics of today's lecture. And today, we're first gonna state some interesting theorems that we need, which is spectral, polar, and singular value decomposition. And after this, we're gonna introduce the trace of operators, okay? And then we're gonna see what a density operator is. We're gonna prove some interesting properties of the density operator. And after that, we're gonna describe quantum evolutions of closed systems, and if there's time, we're gonna go to measurements. So let's start now with spectral, polar, and singular value decomposition, which is chapter 1.2.3. And we start with a theorem. So our first theorem, which is called the spectral decomposition. And I guess you already heard about it. What it says that any normal operator, so any normal operator A on H can be diagonalized with respect to some ON basis. Okay? And conversely, every diagonalizable operator is normal. Okay. So I'm not going to prove this theorem because I want to continue a bit, but you can find this in the reference, namely, so it's on page 72 in the book from Nielsen and Huang. Okay, so let's now see what this theorem tells us. So suppose we have now a linear operator A on H, okay? And suppose that A is normal. Then the theorem tells us that we can find a basis in which this is the operator is diagonal. Means that we can write A as some unitary U times a diagonal U and U dagger. Okay, that's what it tells us. And then last time we've also seen that a unitary is nothing else than the basis transformations. Exactly what it does, it transforms the basis. So we can write U as the transformation from the ON basis V to lambda J. So what we have is that lambda J and Vj are ON bases of our Hilbert space, right? And then what U does is now it transforms from V to lambda. Okay, so I can always write down a unitary in such a way. and D is diagonal. Okay, so it's diagonal, and suppose it has this k. The value is lambda k, which are the eigenvalues on the diagonal. Okay, and with this we can now express our normal operator A. So we can write down A is equal to U, which is sum over j, lambda j, Vj. Then we write D. And then U dagger. Okay, we've just seen how to write the Hermitian conjugate of an operator. So we have to complex conjugate and transpose. Okay, there are no coefficients, so we simply have to conjugate. So we have then say sum over L VL lambda L. Okay, if we write this together, JKL, we have lambda K, and then lambda J, Vj, Vk, Vk, and Vl, lambda L. And then what we see here is this inner product. This gives us a delta Jk. This gives us a delta Kl. Okay, so means that only one summation index remains, and we have lambda k, lambda k, lambda k. So this gives delta Jk and this delta Kl. And this is now a very nice expression because it tells us that lambda k are the eigenvalues, and these cats here, the states, are the eigenstates to these eigenvalues. Okay, and this is usually called the Eigen Decomposition. And either Eigen Decomposition or Spectral Decomposition. Okay. So the spectral decomposition is one of the most important tools, I'd say. Okay, this is what we're going to use all the time. Since most of the time we're dealing with normal operators, means that most of the time we can use the spectral decomposition, and we're going to use this very often. Because writing it down in this form is so useful, and you will see this at some point soon, possibly already today. Actually, already today, like in a couple of minutes. What we're going to continue is, we're going to continue now with another theorem, which is the polar decomposition. It's also a decomposition of linear operators. This is not so famous as the spectral decomposition, but we're also going to use it at some point, possibly later in the lecture. Okay, but it fits here, and I'd like to state this here, the polar decomposition. So it's theorem 1.2. Okay, what it says is that for a linear operator A on H, there exists unitaries there exists a unitary U such that A can be written as U times J or as K times U. So this is equation 1.19. Okay, what's J and what's K? So with J is equal to the square root of A dagger A, which is actually the definition of the modulus of an operator. And K is equal to the square root of A dagger. Okay, and then the unitary U is unique if A is invertible. Okay, so it means now for any linear operator we can write it down in this form, okay, such that we have U unitary and J and K, they're positive, okay, with J and K positive operators. So these are positive. And again, I'm not going to prove this, but you can see a proof on page 78, again in the book from Nielsen and Huang. And a third theorem we now state the so-called singular value decomposition. So suppose, or say, okay, let A be a square matrix. So it means a linear operator, because last time we've seen that any linear operator has a matrix representation. Okay, so we can see a square matrix A is a linear operator. Then then there exists unitaries U and V and the diagonal matrix D with positive entries, so it's diagonal with positive entries. Such that A is equal to U D V. This is equation 1.20. Okay, and the diagonal entries of D are called the singular values. So the proof is not so complicated, so we're going to do it. The reason that it's not so complicated is because we already know the polar decomposition and the spectral decomposition. And we're going to use these two theorems now to prove the singular value decomposition. So first thing is what we note, that for A we can use the polar decomposition, because the polar decomposition says, okay, for a linear operator we can write it in this form. Okay, so means that for a square matrix we can write this in this form. So it means that we're going to write A as a unitary, call it V, and then modulus of A, okay, with V unitary, and the modulus of A positive. So modulus of A is a positive operator, right? This is also what this theorem tells us. Okay, J and K are positive. And so this is by the polar decomposition. And now, since A is positive, it's also Hermitian, and since it's Hermitian, it's normal. Okay. So next, we say that A is positive. This implies that A is Hermitian, and this implies that A is normal. Okay. If I'm gonna prove these two implications in a second, okay, because we are already almost there, and then in the end I'm gonna prove these implications. So if A is normal, we can use the spectral decomposition, because the spectral decomposition says that for any normal operator, we can diagonalize it in some basis. Okay, means that we can write so by the spectral theorem, we can write A as T D T dagger with T unitary and D diagonal with positive entries. Okay, the reason that it has positive entries is because this is a positive operator. So modulus of A is positive, means that it can only have positive eigenvalues, right? So now one more step, and then proving the two implications, and we're done. So we simply now plug this relation in here, and what we get is that A is W, and then we have T D T dagger. Okay, this we're going to define as U, and this T dagger we're going to define as V. So we have U D V dagger, U D V, with U and V unitary, because the product of two unitaries is still unitary. Okay, so what remains are the two implications. I'm going to show this implication first by assuming we have a Hermitian operator. So suppose, okay, say if in K, no, I think we added J, okay, say J is equal to A, then if J is Hermitian, so suppose J Hermitian, means that the inner product of V J V is equal to V J dagger V for all elements of the Hilbert space. Okay? You see it? The reason is Hermitian means that J is equal to J dagger, right? That's what Hermitian means. So then this must hold, right? And what I do now is I use what we know from the definition of the Hermitian conjugate operator. So this is equal to J V V for all V in H. And now what we do is I'm going to exchange these two things here in the argument. And as I've told you today in the beginning, what happens is we get the complex conjugate if we change this. Okay? So what we get is V J V is equal to V J V complex conjugate for all V in H. This means that 0 is equal to V J V minus V J V conjugate. This means that V J V must be greater or equal to 0. So this is all this for all V in H. Okay. So I have here, and I subtract the complex conjugation, and this must be 0, meaning that the real part of this must be 0. The imaginary part must be 0, because the imaginary part remains if I subtract the complex conjugation. And in order for this to hold, means that, not greater equal 0, it must be real number. So in order for this to hold, it must be a real number. And now we can make an implication from right to left and say, okay, if J is positive, then this implies that, okay, if J is positive, we have this here. So if J is positive, then the inner product of JV with V is greater equal 0. Okay, means J positive, and this implies, of course, that this is a real number, meaning that we just proved that if J is Hermitian, so if J is positive, implies that J is Hermitian. This is what we just proved, because this implication just goes from right to left. And now, if J is Hermitian, it's normal, that's trivial, because if J is Hermitian, then J dagger J is equal to J squared is equal to J dagger, right? It means that if it's Hermitian, it's normal. And with this, we prove these two implications, which finishes the proof, right? So the singular value decomposition, you're going to use this in an exercise sheet in order to prove the Schmidt decomposition, right? We're going to speak about the Schmidt decomposition next week. And at an exercise sheet, you have to prove this, and you can prove it by using the singular value decomposition. Okay. So with this, I'd now like to come to traces of operators. So far we spoke a lot about linear operators, and we've seen that they have a matrix representation, and now we'd like to see whether we can also perform trace operations on these linear operators. Okay. So this is next chapter 1.2.4. Trace of operators. And we're going to start with the definition of traces of operators. Definition, I think it's 1.10. And okay, it says that the trace of a linear operator H on A on the Hilbert space H is defined as the trace of any matrix representation of A. So what does it mean? That is, suppose that Vj is no n basis. Then the trace of A is sum over j Vj A Vj. It's equation 1.21. So, and this holds for any ON basis, right? You can choose any ON basis you like. And this is how we define the trace of a linear operator. And in order to see that this gives the trace of the any matrix representation, it's what we're going to do next. So let me first clean the board. So from this equation 1.21, it's not exactly clear that we get the trace of any matrix representation of our linear operator. But if you now use the outer product representation in a particular basis and plug this in, then we're going to see it. So suppose that A has the outer product representation sum over jk a k j w k wj, where our w's are no n bases. Now let's plug this in here. So what we see is that trace of A is equal to sum. Okay, I choose J. Let me choose here J prime in order that we don't have a conflict with summation indices. So we have sum over J, then Vj, and now we plug this in here. So we have sum over J prime K A K J prime Wk Wj prime, and then Vj. So we bring this sum out here, J prime K, then we put the scalars in front, so A, K, J prime, and then we have Vj Wk Wj prime and Vj. Okay. So what's here, these are two scalars. Okay. This is a scalar because it's in the product, and this one. So what we can do is we can flip those. Okay, we can now flip those two scalars. And get Wj prime, Vj, Vj, Wk. And what we do next is we do this, we put the sum in here, okay, because these are the only indices j that we sum over. So we can write this as sum over j prime k, a k j prime, and then w j prime, and here sum over j, vj, vj, and wk. Now last time we've seen the so-called completeness relation, which is exactly this. So the Vj's are an ON basis. And if I sum over all those brackets, I get the identity. So this is completeness relation. So we get identity, and then we are sum over j prime k, a k j prime, and then vj prime, vk. Okay. Again, those v's are an ON basis. So let me put up the blackboard. This is an ON basis, means that this gives delta j prime k. And what we get out is sum over k, a, k, k. Okay, and this is nothing else but the trace of our matrix representation. Okay, with this you now see in the definition that this expression exactly gives the trace of any matrix representation. Okay, what does it mean now that the trace of linear operators is defined as the trace of any matrix representation? It means that the trace of linear operators also satisfy the same properties. Okay, so with this we directly find properties of the trace of operators. So okay, let me state this as equation 1.22. And then, okay, what are typical properties? We know that the trace of A times B for two matrices, so the trace is cyclic. This gives us trace of B times A. This is 1.22, I think I could put this A. And then the trace is also linear, meaning that the trace of A plus B is equal to the trace of A plus the trace of B. And for scalar, we have that the trace of Z A is equal to Z times trace of A. And then one important thing directly follows from 22a, so from the cyclic property. So what we see is that unitary transformations do not change the trace of operators. Okay? So suppose U is unitary and A is a linear operator on H, then a unitary transformation, by this I mean that if I transform a unitary as U, A, U dagger, okay, this is a unitary transformation of my operator A. If I now use this cyclic property, I get trace of U dagger UA. Okay, now I know that U is unitary means that this gives me the identity. u dagger u is equal to the identity if u is unitary. So I get the trace of A. This is an important relation. So it tells us that performing the trace does not depend on the basis. Okay, we can perform any basis change by a unitary transformation, and the trace remains the same. So I would suggest that we're gonna make a break now. It's a good point to do a break. And after the break, we're gonna discuss density operators, right? So see you in 5 to 10 minutes, 10 minutes. From now on, if I don't explicitly say that an operator is linear, you can assume that it's a linear operator. And we are coming now to density operators, which are of course linear. So chapter 1.2.5. So in the very beginning, when we stated the first postulate that we have in quantum mechanics, we said that the physical system is completely described by a state vector, which is an element of the Hilbert space. And then in parentheses, we said that actually it's completely described by a density operator, right? And the reason is that a state vector does not completely describe the physical system under certain conditions, okay? So in order to motivate this now, suppose that there's Alice and Bob. So in quantum information theory, you often speak about Alice and Bob as two parties, right, which, for example, communicate. And instead of saying A and B, we say Alice and Bob. So suppose there's Alice and Bob, and suppose that they communicate in such a way that Alice is preparing a state and she's sending it to Bob, okay? And Bob only knows how she is preparing the state. And how Alice prepares the state is such that she's throwing a coin, and if this coin is heads, she's preparing a state psi1, and if the coin shows tails, she's preparing a state psi2. So means that with probability p1, which is a half for a fair coin, Alice is preparing the state psi1, say, okay, it's psi heads. And with probability p2, which is 1/2, she's preparing the state psi2, which is tails. And then she's preparing the state and she's sending it to Bob. And Bob doesn't know the outcome, but he knows that Alice knows the outcome and sends the state. So we can now ask, okay, how can we describe now this state that Bob gets? Okay? Can we describe this state by a state vector, so an element of the Hilbert space? Can we find a state phi which describes this? So a guess would be, okay, big question mark. Does this state describe the state that Bob receives? The answer is no. Okay, so a big no. It's not the answer because this is a coherent superposition. Okay. There is some phase information in between state 1 and 2. But Bob gets an incoherent state because Alice already measured it and then prepared it and gave the state, so it cannot be a coherent superposition. And the reason is that Alice already knows the outcome. Okay, the outcome is already part of our physical reality. In order to describe this properly, we need composite systems, what we're going to discuss next week. Okay, only if we know how to describe composite systems, we can make this fully plausible. But for now on, I think it's fair enough to state that the reason that we cannot describe it in such a way is that the outcome of the state, whether it's psi1 or psi2, is already part of the physical reality. Okay? In this case, this would describe a state where it's yet not known, so there's nothing that describes whether it's psi1 or psi2. So it's yet not part of our physical reality. And in order now to describe such a, we call it an ensemble, okay? So it's an ensemble of states where the state psi1 appears with the classical probability P1 and the state psi2 appears with the classical probability P2. This is what we call an ensemble. More general, we say an ensemble Pj psi j. And this is described this is described by the density operator. Sometimes also called simply density matrix. Okay, formally speaking, then for a density matrix, you need a matrix representation. But usually people call both a density operator or a density matrix, so this is used exchangeably usually, but actually there's a small difference. So the density operator does describe now such an ensemble, and we usually call this rho, and it's sum over j, classical probabilities pj, and then psi j, psi j. Okay, this is equation 1.25. And now you see that there is no such phase information that if I write here a phase e to the I phi, this would cancel already here. So there is no such phase information between psi1 and psi2. And you can see this simply as an incoherent summation of states with classical probabilities. And this is an ensemble. Okay, it's completely different to such a state vector, which is a pure state. Right? And I'm now going to state a theorem which characterizes the properties of density operator. So it's theorem 1.4. And it says that an operator rho is the density operator of an ensemble if and only if that's actually if and only if it satisfies the following properties. First, a density operator must have a trace of 1. And second, rho must be positive. And as we've seen, from the fact that it's positive, it follows that it's Hermitian. So the proof is going to be an exercise. So I just want to remind you that if rho is positive, it's automatically Hermitian. That's what we just showed. But usually, so I write explicitly down Hermitian because often if you have a density operator, you think of an Hermitian operator. But it must also be positive, which is more restrictive. So let's come to the next theorem, which is okay, under which condition is now a density operator a pure state, meaning under which condition is it simply a single state vector, right? So we can now ask, okay, which properties does rho must have such that the ensemble only consists of one single state vector? If it does consist of one single state vector, we call it pure. Okay, so means that the next theorem is, okay, what happens for pure density operators? And the answer is as follows. So a density operator describes a pure state, which means a single state vector if and only if the trace of rho squared is equal to 1. So let's prove this now. Well, in order to prove this, we simply plug in here the expression for the density operator into trace of rho squared. So we simply now calculate trace of rho squared. Now, first is we use the linearity of the trace. Next, we calculate the trace. Okay, and trace can simply be calculated in, if I take this bra vector and place it here. This is actually an easy way to visualize how to calculate the trace. If you take simply the bra vector on the rightmost side and place it as a cat vector on the left side. So you can easily prove this by how we define the trace, right? And what we get is then psi k, psi j, psi j, psi k. Okay, this is what this is actually the modulus square. Okay, because okay, I write it out because in order for you to see it. So this is the complex conjugate of this, which means that we get the modulus square. And this here, since we are considering normalized vectors, the overlap must be smaller or equal to 1. So we have smaller or equal to sum over kj, pj, pk, and this is 1 because the probabilities must sum to 1. Okay? What we used here is that sum over j, pj is equal to 1. So now we can, what we found is the trace of rho squared is smaller or equal to 1. Now we can ask under which condition does it get 1? Okay, it gets 1 if this overlap is 1. So with equality, if and only if psi k, psi j is equal to 1, which means that psi j is up to a global phase psi k, for all jk. Okay, and if they are equal for all jk, then we see that rho is equal to psi, psi, which is pure. So you can actually see it already here. If this overlap is equal to 1, it can only happen if these two states are the same, right? Because they are normalized. And this global phase doesn't matter. A global phase of the states we can neglect because the fact is that here we have a bra and a cat and any phase will cancel out. Means that the equality only holds if they are the same, and if they are the same, all the psi j's are the same, meaning we are not dealing with an ensemble of many states, but only with one single state. So equality holds then if and only if we have one single state vector, meaning that we have a pure state. So this finishes the proof and brings me to some remarks. The first one is that we call the space of density operators we call it D of H. Okay, this is the space of the density operators of the Hilbert space H. Second, we call trace of rho squared the purity of rho, and it satisfies 1 over the dimension of the Hilbert space, smaller equal trace rho squared, smaller equals 1. So we just showed the upper bound, and the lower bound is also easy to show. If you want to see it, do it as an exercise. And then number 3, if trace of rho squared is smaller than 1, then we call rho mixed. So then we call rho a mixed state. Okay. Okay, let me squeeze in here. Let's say this is 4. Number 3, let me squeeze in number 3. If trace of rho squared is equal to 1, we call rho pure. And number 5, if trace of rho squared is equal to 1 over the dimension of H, so the lower bound, then we call rho maximally mixed. Okay, so it's simply how we call the states if they satisfy some specific properties of this trace. The next thing we're going to ask ourselves is this representation of a density operator so a density operator is always related to an ensemble, right? That's what we just saw. We took an ensemble and wrote down the density operator corresponding to this ensemble. And now we can ask whether this is unique. So meaning whether there can be more than one single ensemble described by the very same density operator. And the answer to this question is yes. So there can be different ensembles which are described by the very same density operator. In order to see this, let me do an example. So let me define the states A as the square root of 3/4 0 plus 1/4 1. So the example is now in the Hilbert space of two-level system. And the second state B is 3/4 0 minus 1/4 1. And what we're going to look at now is the ensemble. Let's take a look at the example where we have with classical probability 1/2 the state A, and with classical probability we have 1/2 state B. Okay, and what we're going to calculate now is the corresponding density operator. So let me write it down. The density operator would be, if I use this formula, 1/2 times A plus 1/2 B. And what we do now is we plug this in here. So we have 1/2 and then 3/4 times 0 plus 1/4 1 times 3/4 0 plus 1/4 1 plus 3/4 0 minus 1/4 1 and 3/4 0 0 minus 1/4 1. Okay, let's multiply this out. Here we have 3/4 0 0. So this is this term. And then we have square root of 3 over 4 times 0 1 plus square root of 3 over 4 times 1 0 plus 1/4 1 1. Okay, and if if we multiply this out, then we have again 3/4 0, 0 plus, no, sorry, now here comes a minus square root of 3 over 4, 0, 1 minus square root of 3 over 4, 1, 0, and then plus 1 over 4, 1, 1. Okay, just multiply this out, and now you see that some things are canceling. So this one here cancels with this one, and this one here cancels with this one. And those 3/4 0, 0 and 3/4 0, 0 sum up to 2 times, canceling this 1/2. The same is for the 1, 1 term, so 1/4 and 1/4. Also canceling this 1/2, so we get 3/4 0, 0 plus 1/4 1, 1. What is this? This corresponds to the ensemble. 3/4 times the state 1 and 1/4 times the state 0. Sorry, different. Here's 0, here's 1. So what we see is we have the very same density operator describing 2 different ensembles, this one and this one. So there is not a unique, it's not a unique ensemble which you can associate with the density operator. And this brings me now to the next theorem, namely to the freedom. So which freedom do we have in these ensembles? And the theorem states that for normalized states, psi j and phi j, we'll say phi k, okay, and probability distributions Pj and Qk we have that rho is equal to sum over j Pj psi j is equal to sum over k Qk phi k phi k, okay, if there exists a unitary with elements u, j, k, such that the square root of pj times psi j is equal to the sum over k u j k q k phi k. So this is equation 1.28. Okay, and if the ensembles have a different size, right, what we're simply going to do is we extend the smaller one with elements having 0 probability. Okay? and a smaller ensemble with entries. So what I showed you here was just an example, okay? And from this example, we've seen that there is not a unique ensemble that I can associate with the density operator. And the theorem now tells us under which conditions you can associate a density operator with different ensembles. So they must be connected by such a unitary U, and I'm not going to prove this here. So for a proof, please see page 104 in the book by Nielsen and Huang. So possibly it's good to think about this a bit and digest it. Because it's not so trivial that it's not in a one-to-one correspondence. So far, we only stated a single postulate, namely that our state space is a Hilbert space with the inner product. And now I'm continuing with our second postulate, stating how states evolve. Okay, so we come to chapter 1.3, which is evolution and measurements. And we start with evolution, so 1.3.1, evolution of states. And how states evolve is captured by our second postulate of quantum mechanics. So we have postulate 2. Saying that the evolution of a closed quantum system is described by a unitary transformation. And the state vectors psi and density operators rho, they evolve according to psi goes to psi prime, which is a unitary acting on psi, and rho goes to rho prime, which is a unitary transformation of rho. So this is equation 1.29, where u is unitary. So you might wonder, how is this unitary evolution connected to some equations that you know from quantum mechanics, namely Schrodinger Equation and von Neumann Equation. So the reason that we stated here as being a unitary transformation is that in quantum information theory, we don't care actually how the quantum systems, how the quantum hardware that we use, how this implements such a unitary transformation. So we are not thinking what can we do with our quantum hardware. Instead, we're just saying, okay, we consider a unitary transformation because a closed quantum system must transform unitarily. And no matter in which system you're working, this is how it is in general, right? And if you now go into the lab and you want to perform such a unitary transformation, you actually rather think in terms of an Hamiltonian. So you usually describe your system by an Hamiltonian, which tells you actually, okay, what can I do there? And given this Hamiltonian, you then have the Schrodinger equation or von Neumann equation, which tells you how this evolution works, right? So let me only in order to capture this, let me also state Schrodinger equation here. So say, given an Hamiltonian, H of my quantum system, or let me say of my physical system, the evolution, say the unitary evolution, is according to the Schrodinger equation. So it's I h bar e over dt psi h psi. It's equation 1.30. Or von Neumann equation. Which is d over dt rho equal to minus I over h bar h rho. Which are solved by the unitary u is equal to e to the minus I over h bar, and then h times t. Let's give this an argument, u of t minus t naught, t minus t naught. Okay, if you solve these differential equations, you're going to see that it is solved by this unitary, and that this exactly describes that the states in a closed quantum system evolve unitarily. Okay? In this lecture, we are not caring about Hamiltonians, so the only thing that we have to think about is unitaries. Now we described states, and we also described how they evolve. And the next thing is, how can I measure this? Or what's the outcome if I perform a measurement? So it's the next section is quantum measurements. And what the outcome of a measurement is again given by a postulate of quantum mechanics, which is postulate 3. And postulate 3, the measurement postulate, tells that quantum measurements are described by a set of measurement operators. So I usually denote these measurement operators by capital M. And these measurement operators, they must satisfy the so-called completeness equation. Meaning that if we sum m dagger m over all m's, we must get unity. And here, the indices m, they correspond to the different outcomes in our experiment. Okay, so now, suppose now I have a state rho that I measure. So if the state immediately before the measurement is rho, then first the probability to get the outcome f, m to get the outcome n, is p of m is equal to the trace of m dagger m rho and the state after the measurement which we also call the post-measurement state. Is given by m dagger rho m divided by the probability. So this is equation 1.33. Okay. Yeah. Okay. Now you might wonder why we need this completeness equation. And as we will see now, the reason is that the probabilities must sum to 1, because otherwise we have a problem. So let's do some remarks. First is the completeness equation here is, as I said, in order that the probabilities sum to 1. So let's take the probabilities and sum over all m. Let's plug this in. So we have sum of trace m dagger m row. Now we use the linearity of the trace. Well, and this must be, of course, 1 for all row. And here you see why we have the completeness equation. This gives unity. And we've seen that a density operator must have trace 1. Okay? So this can only hold if for all row if the completeness equation is fulfilled. So the necessity of having this in our postulate is that probabilities must sum to 1. Second, okay, what happens if I have pure state? So for pure states, rho is equal to psi. We have that the probability is given by psi m dagger m psi, and a post-measurement state. So and post-measurement state is m psi over square root of p of m. Okay, this is simply this postulate used and plugged in rho as a pure state. Now, let me finally provide you with an example. So suppose we have a two-level system. We have an n basis 0 and 1, and we perform a measurement with measurement operators 0, 0, and 1, 1. Okay, first we check whether they satisfy the completeness equation. So we sum over all outcomes m of, so this is our m0, and this is m1, m dagger mm, which gives 0, 0, and then the dagger of this is the same thing, plus 1, 1. So this here gives 1, it's also 1, which is 0, 0 plus 1, 1. And by the completeness relation of our basis states, we have unity here. So this is a valid set of measurement operators. And now suppose suppose we measure the state psi is equal to A0 plus B1, where A and B are complex numbers, and their modulo square sum to 1. Suppose now we measure the state, okay? And we can then ask, okay, what's the probability that I get 0? So it's trace of 0, 0. This is m dagger, and it's also m dagger m, as we've seen here. So m dagger m is also 0, 0. And then psi, which is 0, sorry, yeah, 0 psi. That's a probability. No, it's something wrong. It must be psi, sorry. And this is so this is simply plugging in this equation here, okay, where rho is equal to psi, and then we performed the trace. The trace gives the modulo square of this inner product, and the inner product is simply, if I perform this inner product here, it's what I simply get A. Okay, because 0 and 1 gives 0, gives 0, and 0 and 0 gives 1. So I get up with A squared. So this here, this coefficient, the modulo square of A, is the probability that I measure 0. Pretty intuitively. Okay? And the same for P1, I get B squared. Okay? Then what's the post-measurement state? Okay, it's actually here. You can use this formula here. The post-measurement state is so for 0, the post-measurement state is, so suppose we measure 0, or we measure m equals 0, then the post-measurement state is 0, 0, acting on psi divided by this probability, then the square root, which is modulus of A, and this here gives me A times 0 divided by modulus of A. Okay, so A is a complex number. I can write A as modulus of A times e to the I phi A. Okay. So this gives me e to the I phi A 0. And this is a global phase. Global phases can be neglected. So this is essentially 0. So if we measure the outcome m equals 0, the post-measurement state is 0. This is what we expected. And the same thing is if we measure the outcome m equals 1, we get as the post-measurement state 1 up to a global phase. Okay, with this I'd like to stop for today and see you next time.